So I went to a conference in Washington, D.C. last weekend, well, Thursday and Friday. Of course, I didn't leave my couch. Here. Oh, did you already send it? Oh, you got papayas too. That's okay. Very kind. But the conference was on thank you. It's on well, STEM education of sorts. And interesting fact, I think, did I tell you guys? I don't know if I told you this, but only 1/3 of students that start in STEM graduate in STEM. A huge number fall out. And I've been thinking about that a lot. And I mean, the speaker's point was, of course, that, we're doing a really crappy job of supporting students. So, and I mean, I think about myself and like what I want. I mean, I want to see more people get through, of course. And I mean, of course, I'm not going to do it by lowering the standard, of course. I mean, because if you just go on, you're going to get slammed later. But I mean, if anyone ever needs anything, hopefully, I got that mantra for you guys. If you ever need help with school or other stuff, let me know. I mean, that's way too low to have. And then I also, I don't pride myself in the number of people I fail. Actually, whenever a student drops, I'm like, crap, or at the end of the semester, I'm always, come on, more people getting A's, kind of thing. Some people, I mean, most professors are the positive type. Some people just like, haha, I'm really hard and no one can pass my class. I'm not like that at all. So I want to see you through. And not only that, I mean, whatever skills you learn in this class, I want you to transfer to other classes. So so I mean, if you do struggle, it's more like, if any of you have struggled and you talk to me, I'm always like, okay, what's the strategy? Let's strategize how we're going to get around this. So, and then like if you're wondering my ulterior motives, it's to help you not only in this class, but future classes. So we want to get more than 1/3 of you guys through. So does anybody have any questions? Like I already answered that. Anybody have any questions? Okay, so where we are at, we're talking about kinetic molecular theory. And there are 3 main points of kinetic molecular theory. It's that gases themselves have no volume. The gas has a volume, but the gas particles themselves have no volume. Kinetic energy is proportional to temperature. That's the definition of temperature anyways, so not a big deal. And the last one is that all collisions are completely elastic, meaning there is no attraction between particles and or the wall. And that's important because if there is attraction, the number of particles would seem to decrease if there was an attraction, because then like with acetic acid, having 2 molecules, instead they like to hold hands and walk around in gas. So, okay, and that's building up to the ideal gas law. We're not going to derive the ideal gas law, but the ideal gas law, it's sometimes it used to be called the perfect gas law. Like, what is the perfect person? What is the the perfect teacher? What is the perfect class? I mean, at the risk of sounding pessimistic, you'll never reach it, kind of thing. The ideal gas, the perfect gas, doesn't exist. You might argue helium is about as close as you can get, but the ideal gas does not exist. And we'll talk about real gases later on today. But then we were talking about temperature and what temperature means, and it's a distribution. So where you get a bunch of different distributions, but you have this point on the top, it's the root mean squared. And here we bring it up again. And for some reason in chemistry, we use U for velocity when everyone else uses V. So root mean squared velocity. And what is root mean squared? Well, you take the velocity and you square it. And you take the average of that, and then you take the square root of that. So why do you square the velocity? Why do we do all this crazy stuff? Because velocity is directional. So it's a vector, meaning it can be positive and negative. And how do you get rid of negative signs? You square it. So as long as it's not an imaginary number, and these are real numbers, as long as it's a real number, and these are all real numbers, it gets rid of the negatives. So I mean, you technically should, when you give someone your speed, well, I guess your speed's the magnitude. If you're saying, where are you going? You should say, I'm going 25 miles an hour south-southwest. So that's your vector, that's your direction and your magnitude of how fast you're going. So, but with velocity, it includes the direction. So you square it to get rid of that negative sign. And I already mentioned the average kinetic energy is 1/2 mv squared. And well, you're just squaring the root mean squared velocity. NA, that's Avogadro's number. And so this is another, I mentioned we're going to do, well, these are derivations. So, and this is, so equation there, I guess it's 5.24, and actually should be 6.24 from an earlier edition. The average kinetic energy is 3/2 times R, gas law constant, times temperature. And if you do all that, you can solve for the root mean squared velocity to be the square root of the numerator 3RT over the molecular weight. So that script M is the molecular weight. And I mentioned before, units on R, we have to use different units on R in this one. Use 8.314 joules per mole Kelvin. And so I'll explain that in the problem. So we have a problem here. So what is the root mean squared velocity of oxygen molecules at 25 degrees Celsius? So funny enough, I actually don't memorize, like if you're wondering how my brain works, I don't memorize a joule as a kilogram meter squared per second squared. So I always do this way. Force is mass times acceleration. And so mass is kilogram. Acceleration is length divided by time squared. So the force, a force of 1 Newton is a kilogram meter per second squared. And a joule is a Newton meter, if you learn that in physics class. So a force of a Newton over the distance of a meter. So a joule is so kilogram meter squared per second squared. And if you wonder what a watt is, next thing is a watt is a joule per second. So a watt is a kilogram meter squared per second cubed. So, but I know that's physics, but for this class, you can just, I mean, everything is open book. You can just know where everything is at. But okay, so calculate the root mean squared velocity. And one thing to note, there's 2 values of R. So, and look at the units, we have 0.08206, and that's liter atmosphere over mole Kelvin. And you have 8.314 joules per mole Kelvin. So which one do we use? I'm gonna use this example to show you have to use the 8.314. So root mean squared velocity, so you have 3RT. So 3R, 8.314, and joules per mole Kelvin. Temperature 298 Kelvin, all over. So molecular weight, and oxygen is 32 grams per mole, which is 0.032 kilograms per mole. And if you didn't know, square root is the same thing as raising to the 1/2 power. So let's look at the dimensions. So let's just look at the units. So first of all, notice the kelvins cancel and the moles cancel right there, or the inverse moles, I should say. So we're left unit-wise. We have joules per kilogram, the 1/2 power. And a joule is a kilogram meter squared per second squared, all over kilogram. Sorry, so that's just inputting the joule to the 1/2 power. And what cancels? I guess I can change colors. I'll go black. Kilograms cancel. And we are left with meters squared per second squared, square root, which equals meters per second. So that's the reason why we have to use the mass, the molecular weight in kilograms per mole, because of the units, and also we have to use R in the joules per mole Kelvin, because to have the units all come out. If you don't, then you get some really, you'll get a number, but you'll get some really weird sort of like answer in terms of the units. So you have liters, it'll have atmospheres. So I mean, really, these numbers mean the same thing, but the units are different. I mean, in liters is a volume, atmosphere is its pressure, it's force divided by area. So, I mean, this all relates. So it's unit wise energy. So volume times pressure is in fact energy. But I mean, it unit wise it makes sense. But I mean, in terms of like how we think about things, I don't think of energy as volume times pressure. I think of it as forced by a path length. So I mean, it'll work out, but it's kind of weird. But hopefully you can see here is that the units work out to meters a second. And then the next, so you got the units down. So then the next thing is you just put in this number in your calculator. And what is it? It's going to be 482 meters per second. So, and that's just 3 times 8.314 times 298 divided by 0.032, square root of that number. And you get 482 meters a second. And so this is fast. So 482 meters a second. I guess maybe I should have done the Socratic method. Is that fast or is that slow? It's fast. This is a third of a mile a second, right? So half a kilometer, about a third, maybe a little bit more than a third of a mile. So in 3 seconds, can you imagine if you could run in 3 seconds, you've gone a mile? You know, that beats my 10-minute mile jog that I do in the morning, right? So, you know, so who's that? Oh, okay. Yeah, we don't have the speed dimension or whatever he calls it to draw upon. Well, that would be slow for the flash. But so 1 mile in 3 seconds, you know, assuming a straight line. That's fast. And the other thing, if you look at this number, this breaks the speed of sound. So why are we not hearing sonic booms right now from, although I guess it's about, maybe it's a little less than 298 Kelvin in here. It's probably about maybe 24 degrees. It's kind of warm in here. So it could be, actually, maybe it's warmer than 25 degrees. Anyways, why are we not hearing sonic booms from the oxygen molecules? And the nitrogen's even lighter, so it's gonna be going faster. So why are we not doing that? Well, because so remember what sound is. Sound is it's a pressure wave. So, and it's coming towards you guys. So it's a longitudinal wave. And if you have something big like a fighter jet, and if it goes faster, it can break the pressure wave, and then the sonic boom. Has anyone ever heard a sonic boom before? They're loud. So spoiler, loud. And we used to hear them sometimes, like on Oahu by Pearl Harbor. I heard them a few times. I went to University of Dayton for undergrad, the Wright-Patterson Air Force Base. Sometimes they would fly the jets really fast. They're loud. They're really loud. But the oxygen molecules are just not massive enough. So, and you're going to have, and again, this is the peak. So the velocity kind of fits this curve. This is just the peak. You're going to have some going faster. All right, recap for this one. How do you calculate the root mean squared velocity of something? You use the given equation, square root of 3RT over molecular weight. Things to remember, use the 8.314 for R, use the molecular weight in kilograms per mole. And the reason for using those two units, or using those two values, are the units, so that the units cancel down to meters per second. And then when you throw in the numbers, you get 482 meters per second for the root mean squared for velocity for oxygen. So, questions? I mentioned that's fast. That's pretty fast. And gases, so I know this is kind of a box, but it helps actually if you, for me at least, when I make the sound effects. So if you have a gas particle, something like I don't know, like propane tank. So I think about this sometimes, the gas in the propane tank, and it goes pew 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 pew. It flies all over the place. This is the path that it takes, right? So it's going all over the place. That's the path. And like I said, you got to use the pew 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 pew. So and I mentioned, so half a kilometer a second for an oxygen molecule. on average at this temperature, it's not just going a straight line because it's colliding with things. It's trying to go in a straight line, it hits another molecule and it goes this way or hits the wall and it's flying all over the place. So that's what I mean by the mean free path, the typical molecule path. So also, if you ever look at gas cylinders, so like when you see like a propane tank outside of a house, it looks like a Tylenol, right? So it's got kind of the whatever cylinder that looks like a cigar. I guess sure, it can be cigar shaped. What the heck, right? So you see the cigar shaped. It's, I guess I was kind of say a cylinder, but you have a cylinder, but then you have the head on both ends. So and the reason why you have them in that shape is because of something called hoop stress. Because when you have gas particles and they're colliding with the walls, and it lets the cylinder or the gas container expand. So you have to have smooth edges. If you had a box like this, actually, you'd get cracks on the edges and corners. You would probably get cracks there from the gases going and pushing the metal out. If you have like a square edge and you push it out, it's going to cause usually a fail right along there, along the corners. So, and that's among other things. There's just imagine a lot of gas and a lot of it moving around, hitting everything, smacking around. That's where we have that. So that's the mean path. Okay, and moving on, talk about a concept called a fusion. And maybe you've noticed this. Just over time, your tires deflate. I mean, actually, my tires are pretty good, I guess. I've only had to fill them like 2 or 3 times. Of course, the temperature doesn't change that much here in Hawaii. In the mainland, it's always been like if you live in the mainland, especially somewhere cold, you have to add more air in the winter and you have to take air out in the spring. That's just because of temperature. But I mean, here in Hawaii, of course, the temperature doesn't change that much. But over time, your tires lose air. And also with balloons, like you blow up a balloon over time, the balloon deflates. So the metallic balloons, those stay. Actually, it's amazing how well they work. When I was a kid, you had a helium balloon, like the thing would deflate after like a day at most. Now those metallic balloons, they float for like a week now. So, but the gases, they find their way through little cracks. So in your tires, there's little tiny holes. Sometimes, just in the rubber. Sometimes especially around where the valve is to input air. But the gases will move. They'll effuse through those little tiny holes. And if you have a gas, and again, it's not going to be in a box, but if you have a bunch of gas in a container, and if you poke a little hole into it, the gases escape. And you've already learned, right? So the velocity, root mean squared velocity, RMS velocity, it's 3RT over the molecular weight square root. So the rate at which gases effuse is proportional to 1 over the square root of the molecular weight. And Graham, so Thomas Graham went ahead and noticed if you have 2 gases, the rate of gas A effusing with respect to the rate of gas B is the inverse of their molecular weights, square rooted. So not surprising, it's just the root mean squared velocity. So, and this is one way you can purify gases. So if you ever wonder why, so purifying certain gases, and where I'm also building up to, this is how we purify uranium to make for nuclear reactors and nuclear weapons. So using this idea. Okay, so let's look at Graham's law of effusion. An unknown gas effuses a rate that is 0.462 times that of nitrogen gas. Calculate the molar mass of calculate the molecular weight of the unknown gas. So your rate of A over rate of B. So You can look at it that way. So the rate of the unknown all over the rate of N2 equals the square root of the molecular weight of nitrogen all over the molecular weight of I'm just using X for the unknown. So on the rate of the unknown versus the rate of nitrogen, it's going to be 0.462 is equal to square root of molecular weight of nitrogen is 28 grams per mole divided by X. So I'm just, using X for my unknown. So you square both sides, 0.462 squared equals 28 over X, which means X is 28 over 0.462 squared. If you do that, you get 131 grams per mole as your answer. I know I dropped the grams per mole in that, but so hopefully that's pretty easy. You can see you just kind of rearrange it. And 131, that's probably xenon. So, I mean, it may not necessarily be xenon, but if you look at xenon there, I don't know if you can see, it's 131.3 grams per mole. So it's probably likely to be xenon. Although that's hard to tell because xenon is not very reactive. It's going to be, I guess you could do spectroscopy on it, but xenon, since it's a noble gas, is not terribly reactive. But what you could do, you could breathe it and see if it gets you high. Xenon actually gets you high.
Like helium?
Helium gets you high. Oh, helium, you can displace oxygen, that'll get you high. Or you can make your voice really light. But no, xenon will actually get you, it's a approved form of anesthesia, like laughing gas, like nitrogen, nitrous oxide. So we're actually looking to use xenon for lung imaging. So I had a friend that was doing that in graduate school. I don't think that's gone anywhere though. But anyways, for this one, I don't know if you really need a recap for this one. This is just applying Graham's law of fusion and solving for the unknown. So questions with this one? Okay, let's see if you can figure this out. So uranium-238 hexafluoride and uranium-235 hexafluoride, you can use that to enrich uranium. How much faster does uranium-235 hexafluoride fuse than uranium-238? So uranium-235 is the nuclear fuel, and 238 is also known as depleted uranium, or it's well, you can't typically use it for a nuclear reaction. But I'll give you a hint. So it's going to be 238 plus 19 times 6 all over 235 plus 19 times 6 square root. I'm sitting on a lot, but I actually have a lot of energy today. I've been feeling a drag lately, so I ate some sugary cereal before class, so I got lots of energy with me right now. Now I got water in my mask. Awesome. Some people think A, 1.004. Some people think B. Some people think C. Some people think D. Is anyone getting an answer that's not there? Most of the class is going for A, and A is the right answer. Oh yeah, all right, thank you, Kiani. So is anyone getting stuck? If so, I want to see you input it into your calculator. No one's. Okay, and there is a so what with this. This is how we enrich uranium. Uranium, when you dig it from the ground, it's about 0.7% uranium-235, and the rest uranium-238. And it depends on where you're at. If you're in Canada, they just take the uranium and you, what you do for nuclear reactors, you turn into uranium oxides, you oxidize it, you make pellets of the stuff, and you usually encase them in something, a really high melting point material like niobium or something like that. And then they're kind of like hockey puck cylinders, and you create what's called the pile. You pile them, you stack them up on top of each other, and then you have control rods that go in between them for a nuclear reactor, and you have a fluid in between them to mediate it. In Canada, they use heavy water, so deuterium 2 oxide, and you don't have to enrich uranium if you do that. We use light water or just regular water in the United States, and we usually enrich our uranium to 3 to 9%, depending on the nuclear reactor. And this is partially an issue because if you go to Iran, I guess it's the proper way to say it, Iran, they're enriching their uranium past 20%. And they're like saying, no, it's for civilian purposes. And yeah, that's complete and utter BS. So, I mean, we know here in the States that you don't have to enrich it past 9%. So anything past 20% is ultra high enriched uranium. And one thing with a nuclear reactor is you don't want it to get very hot. So nuclear reactors, they're actually not very hot. So they usually don't get hotter than, say, 500 degrees Celsius. And a candle flame is 550 to 600 degrees Celsius. So a candle, thermal wise, is hotter than a nuclear reactor. Of course, like in a nuclear weapon, you can get temperatures, well, hotter than the sun even. So you can get them really, really hot. But with a nuclear reactor, you're not trying to generate a dangerous amount of energy. You want it to be slow and controlled. If you increase the enrichment, you increase the temperature, which means you have to have a much tighter control system. So it's a really stupid way to make power. If you wanted to really heavily enrich uranium to generate electricity, it makes the safety go way down, and it makes it a lot harder to control, which actually ends up losing money. Are there applications where you need to have really heavily enriched uranium? Yeah, absolutely. In military craft, so nuclear submarines, like the nuclear reactor in a submarine is about this big. So I'm holding up a half-gallon bucket. So I mean, the nuclear reactor in a sub is not very big, but then there's a lot of controls around it to make sure that it doesn't go out of hand. So they do use weapons grade uranium in those. Do you have a question, or you just?
Yes, and yeah, I was just searching for how big is the uranium chunk they use for the engine?
I honestly don't know, and it's probably classified. It's going to be on the order of tens of kilograms. So probably somewhere between, if I had to guess, somewhere between 30 kilograms and 100 kilograms. So about maybe twice the volume of this, 2-ish liters. So I don't know if you're asking for mass, whatever the density of uranium is. So I guess that would be closer to, actually that'd be closer to 30. All right. Other questions? All right, then going on to real gases. as promised, we'll talk about real gases. Okay, I'm not going to test you on real gases. Just so let the record state, you are not tested on real gases, but you may have to learn about real gases later. And I mentioned before that the molar volume is 22.4 liters. Well, I guess it's 22.41. So, and if you look at the molar volume versus other gases, you don't quite get there, except at 0 degrees Celsius and 1 atmospheric pressure. The only one that gets, well, I mean, a lot of them get close. I mean, these are pretty close. See how close nitrogen is? Helium is spot on. Helium is about as close to an ideal gas as you'll ever get. But the volume is slightly different. And also, why does this happen? Because, well, this one here, well, the volume is kind of tweaked a little bit because of the attraction, well, because of the attraction between the particles, except for hydrogen. I guess it's the particle size that pushes it over. But some of the other non-ideal behavior is the effect of the volume. So if you take a gas, and an ideal gas, if you put infinite pressure on it, it would go to 0 volume. So, as you start getting pressure to a real gas, so like argon, ideal gas versus argon, and argon's a pretty close to ideal gas, but under enough pressure, the particle size gets into the way, and then the volume of the gas is higher than actually would be ideal. And that has to do with the actual fact that there's a particle there. So when I say volume, right, you take and you compress things down, you take gas, you compress it down. Eventually the size, the actual, the electron cloud in the nucleus of the atom is going to start pushing up against the other electron clouds and nuclei of the other atoms. And then it actually is going to come into some other space issues. So when we're at 1 atmosphere of pressure, we're actually at pretty low pressure for ideal gas laws. And so air at this temperature and pressure acts very ideally. So non-ideal behavior also intermolecular forces. So xenon is an ideal gas, or is a noble gas. It behaves pretty ideally. We haven't talked about intermolecular forces. We'll talk about that next semester. But there's an attraction between particles, and xenons. Think of atoms as this big kind of ball of negative charge, electron charge. When you have 2 xenon atoms approach each other, the electron cloud of this one interacts with the electron cloud of this one, and it warps it the other way. Now there's a positive charge, and then this one gets kind of close to it. And so now there's a negative charge here, and there's a slight attraction. That's called a van der Waals force. So, and there's a slight attraction between 2 xenon atoms. And so that causes it seems like the number of particles has decreased. So it's sort of like the number of moles of xenon has gone down. So the pressure goes down for that. And the textbook goes over this, the van der Waals equation on this. And the van der Waals equation, this is a horrible equation to use, and I have not assigned any problems. If I have accidentally assigned you a problem, let me know. I'm pretty sure I didn't. But if I have accidentally assigned you a problem, let me know, and I will delete it as fast as I can, because these things are a pain to solve. I mean, you can solve them, but if you solve for volume or number of moles, you have to do it through an iterative process, and that's just a royal pain in the bum. So, but why am I teaching it though if I'm not going to use it? For one thing, I'm supposed to. Second thing is because it tells you what an ideal gas is and what is not. And the van der Waals came up with these correction terms. So instead of PV equals nRT, you have P plus some constant A times the quantity n over volume, number of moles over volume squared, and times the quantity volume minus number of moles times the B, the correction factor for the particle volume, equals nRT. So it's just shifting it that way. And to be honest with you, there are much, much better ways to deal with real gases than the van der Waals equation. So real gases are an issue. And if you go further into engineering, there's significantly easier ways to deal with it than van der Waals. So no one uses van der Waals, to be honest with you.
Who's the first to kind of figure it out?
I'm not sure on that. He might have been. So the my favorite is K's law, which is PV equals Z nRT. And this is called, you just put a factor in front of it that accounts for everything. This is called the lump sum approximation. We just take all your variables and you throw it into one sum and you just, take some experimental data and then just make a chart of the factor that you need to worry about, and then just kind of know which factors work under certain circumstances. And so it's a semi-empirical model. So we'll talk about that more next semester. But that's my preferred way of dealing with ideal gases. So that's also the easiest way. It's also easy to program in something like Excel. But there's better, like I said, there's better ways to do it. And man, we have blown through this section. So questions? If not, I'm going to go to thermodynamics. I kind of thought we'd hit thermo anyways. So thermodynamics, and I guess you weren't privy to some of the conversation earlier. So Andre here was asking me like some of the things I don't like about my job, like, oh, the beginning of the chapter 1 stuff. Like, there's things that I hate worse than that even. Actually, chapter 1's kind of cool. It's like the philosophy of science. I don't like thermodynamics. So, but the nice thing is students love thermo because it's very, very straightforward. And I can tell you that that one of the hardest things about thermo is defining the system, and I'll get into that soon. So I guess I should backtrack. So this chapter, so we're moving on to the next chapter. This next chapter is on the next test. This upcoming chapter, it's on the next test. And the test is 3 chapters. So 5, 6, 7. But okay, so let's talk about energy. There's a couple of different definitions for energy. I guess I kind of told you the physics definition. So force times the path length. This is, we can also call energy the capacity to do work. So I don't have any kids, but I have nieces and nephews, and I always see how much energy they have. Like, oh, you guys have so much energy. So what can you do with that energy? Like, they can do the dishes, they can do the laundry, that stuff. They can do work. But of course they don't. Right? They're kids. They just run around, bounce around, eat a bowl of Lucky Charms and run around. So, but they have the capacity to do all their energy, right? So energy is the capacity to do work. There's other definitions, of course. And then I already mentioned the dimensionality of a joule. So there's another commonly used unit is a calorie. I'll talk about that in a little bit. But also, to very simplify things with energy, energy can be kinetic energy, which is the energy of motion, and then potential energy, which is stored energy. Are there more types of energy? Yes, there are. There's electromagnetic radiation, that's a form of energy. So, but trying to keep things simple. Kinetic and potential energy, so everyone is awake here. It's too bad. We can do the classic physics. Gosh, I'm such a physical scientist. Have you ever seen a classic physical thing? Like, this textbook now has stored energy. It has no kinetic energy. You let it go, and the stored energy, usually you wait to see if someone's asleep, and then you slam it in front of the first student. But of course, that's a bit less allowed this day and age. But the stored energy, the potential energy, turns into kinetic energy. Just like for me, I had some cereal before I came to class. So I was dragging on Monday, so I'm like, I should eat more sugar before class. So I'm actually a little hyper right now. I'm trying to catch it, some of it, but I have that energy. I can, I can run around. So that all that energy that's in the granola and sweetened soy milk with sugarcane juice, that all that energy, that potential energy, can be turned into kinetic energy. So stored energy, so food energy, the energy calories are food, that's stored energy, and then we can turn into something like, kinetic energy of motion. Okay, so now we're going to talk about the first law of thermodynamics. Well, actually, I guess I'll think about let's start with the system first. So the law of conservation of energy. So we've heard of the law of conservation of matter. Matter is either created or destroyed. Energy is also conserved. So the amount of energy stays the same, but it just changes forms. So energy will change forms. Energy is not created or destroyed in a physical or chemical process. And we're going to talk about the system. And now we have a dreaded magnitude and directions. So you define your system, and energy flow into your system is positive, energy flow out of the system is negative. And we have that for directionality, and a lot of Thermo is defining your system, and it's picking which system to define. And it's actually contextual. And as you'll see later when we do problems, maybe you've heard horror stories like, oh man, I missed the negative sign that screwed up my entire calculation. This is usually what they're talking about, is the negative sign. And I already mentioned before, negative is 1 half mv squared. So, okay, now I'm going to move on to talk about the first law of thermodynamics. And the first law of thermodynamics is basically a law of conservation of energy. So the first law of thermo or chemistry class is the change in internal energy for the system is equal to the work plus the heat. So I mentioned for chemistry, it depends on which class you take. They may or may not expand upon the first law of thermo. You can include gravitational potential energy, for instance. If you want to do a first law of thermodynamic calculation for like a roller coaster, you would have to include gravitational potential energy. So that's right, because the roller coaster going down the hill, so it turns the gravitational potential energy into work. So you can get work out of other things other than chemical energy. So what I mean by work plus heat. So let's go back to chemistry, not talking about roller coasters. But so you can think about it as like biologically wise. I told you I ate some cereal before coming to class, and so as my body is burning the sugar, it is turning that potential energy that's in the sugar into work, right? I'm moving, and heat, right? So we're warm-blooded creatures, but I mean, in general, whenever animals burn, we even use the word burn, we're not really burning it, we're going through the Krebs cycle, but we're oxidizing fuel, and some of that turns to heat, some of it we turn to work in a really weird way. You can learn that in future classes. So maybe something you know, maybe some of you know this a little better. Think of engines. So a gasoline engine. The way a gasoline engine works is you have a piston, and you have, so depending on how many cylinders you have in the car, I have a 4-cylinder engine in my car, and so you have in your engine you have the chamber and then a piston, and when the piston goes up, it goes down, and while it goes up, your fuel injector will inject gasoline and oxygen into the engine. Piston goes down, the spark plug ignites it, and it pushes the piston up. So there's an explosion. It's an internal combustion engine. It explodes and shoots the piston up by the expansion of the gas. And car engines, they get hot. And they also do work. Work is force. Remember, work we didn't talk about, but I did mention this, but let me just talk about this. Work is force and a direction. You put in a force and a direction. So if it's a car driving in that direction, that's work. So for me, if I'm doing work, I'm taking something and I'm pushing it in some direction. So I can do work. So not only do I have the capacity to do work, I can actually do work. So, and some other things. So how much math do you guys have? Is anyone in the Calc 3 or Calc 4 yet? Is anyone in calculus? So, okay. So internal energy, so as you go further into calculus, you probably know functions. So function of x, and so y is a function of x, and you can have other functions. So you can have z is a function of x and y. So you can have three-dimensional surfaces, not just 2D graphs. So later on, do you know what derivatives are yet, or? Some do, some don't. You can do, if you do partial differentiation, so for a multivariable function, if you do derivation of each of the variables, for a three-dimensional one, for z is a function of x and y, if the derivative of the function with respect to y is the same as the function derivative y to x, that is known as an exact differential. That's also known as something called path independent. So, which means it doesn't matter how you get there. Internal energy, the internal energy of a system is path independent. Work and heat, though, work and heat are not path independent, they are path dependent. So, and that's a connection you'll see later on with mathematics. So, and what do I mean by that? So, if I take a gallon of gasoline and I burn it, it's going to lose the same amount of internal energy. It doesn't matter what I do with the gasoline. If I oxidize, actually burn it. If I oxidize a gallon of gasoline with oxygen, it's going to have the energy change be the same no matter what. So what can I do with that gallon of gasoline? I can take it and I can throw it into, like, put some wicking rags in it and ignore the heat of the rags, but I can light it on fire and I can turn that gallon of gasoline, I'll just give a number, 100,000 joules. It's going to be more than that, but 100,000 joules from a gallon of gasoline ready to heat. I can just turn all that energy into heat. Or car engines tend to be about 20% efficient. I can take that gallon of gasoline and throw it into a car engine, and I can get 20 million joules of work, 80 million joules of heat. So, or I can throw it into a hybrid car. Hybrid car is probably about 35% efficient. So I can throw it into a hybrid car, and I can get 35 million joules of work and 65 million joules of heat. I can throw it into a fuel cell car, which is about 60-ish% efficient. And I can get 60 million joules of work. And I can get 40 million joules of heat. So you see that the energy of the system, the internal energy of the system, at least well for the gasoline, if you define the gasoline as a system, the energy change for the system does not change. But the amount of work and the amount of heat that you get out of it changes. That's what we mean by path dependent. So the internal energy change is independent, but the work and the heat is dependent. It depends on what you're doing. If you just burn it, it all turns to heat. You put it in one car, it'll turn 20% to work. Another car, 35%. Another car, 60%. So it depends on what path it takes, how it does that. And that's what we mean by path dependence. So, question, yeah.
How efficient are nuclear reactors, or did you say that already?
Nuclear reactors, it depends on which one you have. They're pretty inefficient. The ones that we have in the United States, they're around 20%. So about the same with the car. Coal plants are about 30 to 33%-ish. So we at Maui were going to be a little less efficient because we use diesel number 2 for our electricity systems. So we're not very efficient, but we also don't have a lot of load. We only have maybe 350 megawatts that we we generate here. So we have expensive electricity, but we don't have very efficient, but there's no need to invest in it. So yeah, nuclear power, you sacrifice efficiency for safety. So, okay, and hopefully you can kind of figure this one out. This is to keep you awake. So if our internal energy system change is 50 joules and the work is 20 joules, how much heat did you have in that? Everything gets A, 50 joules. Everything B, 30 joules. Okay, everyone's going for 30 joules. Yeah, 30 joules is the right answer. Even Zoom land got that. And so Joule is, that's the SI unit. So the system, the metric system, the system international or whatever it is in French. But there's another unit that you might use, and we certainly use that here for nutritional wise, the calorie. So the calorie is the amount of heat that it takes to raise 1 gram of water 1 degree Celsius. So if you wonder where the term calorie comes from, and you might use this in Chem Lab, we use calories quite a bit. Where we use calories even more is nutritional wise. So, and one thing when you look at food labels, the food labels always capitalize the calorie. You're like, what is capital C calorie? Cal. What is capital Cal? That's the kilocal, the 1,000 calories. So a nutritional calorie is the amount of energy. So it's 1,000 little calories, 1,000 grams. So 1 gram of 1 degree Celsius, that's a little calorie. A nutritional or kilocalorie, that is 1,000 little calories, which is the amount of heat it takes to raise 1 kilogram of water 1 degree Celsius. So, which means like 100 calories, like a chocolate bar, like when you like one of those mini chocolate bars, well, I guess those are kind of medium size, not the mini ones, but the ones that are about 1 inch long. Those chocolate bars that you get for like Halloween, they're about 100 calories. So the amount of energy that's in that little chocolate bar, if you were to burn it, it's equivalent. You could take a kilogram of water, this is the water in this container, and this is about 1 liter. It's 40 ounces, which is a little bit more than 1 liter. You take this much water, and you could bring it from 0 degrees Celsius to 100 degrees Celsius, assuming that all that energy in that chocolate bar went to this. That's a lot of energy. That's a lot of energy. So food has a lot of energy in it, right? So I mean, you think like, oh, geez, like how much energy do you get from food? Like, well, you actually get a lot of energy from food. So that little candy bar, I mean, if you think about like your stove, you turn your stove. If I were to take the liter of water and put it in a pot, and if I had it at 0 degrees Celsius, it would take a while. Like turn the stove on high. It'd probably take like 10-15 minutes to raise this much water to boil on high heat, right? So that's a lot of energy in that little chocolate bar. Yeah, question.
Are people look into using food as a source of energy for like cars or houses or anything?
Oh yeah, absolutely.
So have we gotten anywhere with it?
Well, I mean, there's alcohol-based, like NASCAR runs off of ethanol. I mean, ethanol is for plants. It's just it has to do with, to answer your question though, it has to do with temperature and pressure. Because if you look at the, so Oahu has 100,000 barrel per day capacity. So 100,000 barrels per day, that's 450,000 gallons of fuel per day. And an acre of corn can make 350 gallons of ethanol. So I mean, the output of a farm versus petroleum, it doesn't come close. There's just not enough farmland to deal with our energy usage using that. But you can with solar and or or nuclear if you want an alternative fuel source. Okay. Other questions? Moving on, here's an equation for you. And there's two equations, Q. So Q is heat. So remember, internal energy is work plus heat. First law of thermo for chemistry class. The heat can be described as the heat capacity times the change in temperature, or the mass times the specific heat capacity times the change in temperature. So it depends on your application. Sometimes you use the heat capacity, sometimes you use a specific heat capacity. So what is heat capacity? So things that have very low heat capacity, if you put a little bit of energy into it, the temperature goes up really high, really fast. Or the other way around, take away heat, the temperature drops very, very quickly. High heat capacity, so that means you put a lot of energy into something that's high heat capacity, the temperature goes up slowly. And if you draw energy away for something that has a high heat capacity, the temperature goes down slowly. So with that in mind, water, what do you think? Does water have a high heat capacity or a low heat capacity? Water has a high heat capacity. Doesn't have the highest, but it has a pretty high heat capacity. So meaning it takes a lot of energy to raise water up in temperature. The other way is around is as water is cooling, it releases lots and lots of energy. So, something that has a low heat capacity, metals. Metals tend to have a low heat capacity. So, meaning like, so you can really get metals up to a high temperature really quickly. You put your metal spoon into like a boiling water, that metal, gets to 100 degrees really fast, right? It just sucks up that energy and the temperature goes way up. And then, so I've done this for tricks. Has anyone ever been stung by a stingray before? I have. Or a jellyfish, even. So one of the ways to get rid of venom, I can do this for insect bites too. So protein-based venoms. So if you apply heat to the area, it'll denature the proteins, meaning it changes the shape. And so if you want to deliver a lot of heat to an area really fast and do it to a specific area, what I do is I take a spoon and I put it in a boiling water. One time I got stung by a jellyfish right here. And I remember I was actually swimming in the ocean. I came to work and they're teasing me like, oh, what happened there, Mike? Where were you going? And that's when they told me, I remember they like, okay, well, the way you can get rid of your jellyfish sting is to put a spoon in a boiling water and then just place it on that. And as hot as you can handle, and I do it a few times and it'll go away. And it worked. It works for jellyfish stings, worked for, what is it? Stingrays. So I got stung by a stingray on my finger, believe it or not. Did you get in your foot? Yeah. Most people get stung in their foot. But I'm the, oh, you go, okay. Yeah, I'm not the only one that had this happen to, but it's very rare. My parents, it was right after a hurricane, they were in Florida. I was helping them clean up their yard, and they lived close to the beach, and I was all sweaty. I was like, you know what? I take a shower, I can just go jump in the ocean, or I guess the Tampa Bay. So I went to Tampa Bay and I jumped in and I kind of like started washing off, and in Florida has nice silica sand. I was like going around, I was touching the nice silica sand, and then something got me. I was like, oh man, and it turned out it was a baby stingray, just stung me, and it stung me right in the finger. Man, that hurt. It really hurts. It didn't. I went to the urgent care because the venom started making my heart pound and stuff like that. And but what I did was as soon as I got home, back to my parents' house, I did the trick, the hot water in a spoon. We boiled some water, put in a spoon, and just my dad thought I was crazy. I asked him to take me to the urgent care, and I'm like sitting in the car. I'm like, oh, okay. I was doing this a few times, and he's like, "What are you doing, son?" I was like, "I'm denaturing the proteins, Dad." You know. So I'm not sure. Have you done that too, or did you try the? Oh, it hurts.
Yeah, I heard it hurts.
Yeah. I'm not sure. I've had weird bug bites, but I don't know.
Like I heard you'll know.
Yeah. Then the answer is probably no. Never been bitten by a snake. Probably not a centipede. But the other thing with jellyfish stings, use acid. So, because if the stingers are still on you, you wash the area with acid, that shrinks the cells. So then you can get rid of the venom. So first thing for a jellyfish sting, flush the area with acid. So vinegar or citric acid. So lemons, limes, vinegar, that'll then flush the area, and then you can do heat. And cold if you want for pain. But anyway, so whole point of that was talk about heat capacity. So metals have low heat capacity. Things like water have high heat capacity. So another thing with water having high heat capacity, right? So the metal, you take the metal spoon and you put it on your neck or wherever you got the jellyfish sting, or your finger or foot for the stingray. You're putting a lot of energy in, right? So why use a metal spoon? Well, I could do the same thing. If I was worried about the venom in my finger, I could put my finger into boiling water, right? But of course, what's the problem with that? Well, I mean, you put metal, like 100 degrees Celsius metal on your finger, like, oh, this hurts. And like, oh, it's not too bad. I'm like, that's fine. I'm okay. If you put your finger into boiling water, like, this hurts, it still really hurts. I'm crying from pain right now for 5 seconds, right? Because even away from the heat source, the water is still pushing out lots and lots of energy. So, and if you're wondering why does water have a high heat capacity and metals have low heat capacity, well, it has to do with the molecules. So metals, they're just atoms aligned in straight lines. So it's just a bunch of atoms and a solid. And temperature, remember, is translational energy. So that means that if you have a piece of metal and you increase the temperature, the atoms just move, they're bouncing around in their lattice, So here's cold metal, here's hot metal. It's just kind of moving around. It only goes in translational energy. Water, on the other hand, water has rotational, vibrational. There's water, it's rotating, vibrating, and it has temperature. So it has all these things. So if you have a piece of metal, and you add 100 joules to it, that 100 joules basically just turns into temperature. Whereas water, you add 100 joules, some turns to rotation, some turns to vibration, some turns to temperature. So that means that as water is cooling down, it's drawing on its rotational energy and its vibrational energy to kick out, and it'll give out more and more temperature as it cools off. So, and another point. So when we drive cars, we use antifreeze as a cooling mechanism for a car. The radiator car, we use antifreeze. So why do we do that in Hawaii? So we don't need antifreeze here. I mean, there's lots of places in the country. I mean, it's not just Hawaii. Southern California, it never snows in Southern California. Bay Area. I mean, there's lots of, even with the population centers we have. I mean, the California coast, it never freezes there. And it's never going to freeze there. So why do we put antifreeze into our cars? Yeah, question.
Because the water will get too hot.
Well, you would just make a bigger radiator, but the point is ethylene glycol antifreeze has a higher heat capacity, which means you can have a smaller radiator.
Okay.
So then it becomes a size thing. It makes the cars more efficient, so you have less weight. So yes, you can use water for cars for the fuel, and we do. We use like in a car, you have the radiator. That's what draws heat away from the engine, because told you about 80% of the energy of the gasoline goes in heat. You'll melt the engine if you don't. You'll maybe not so melt. You'll blow a gasket head, which means that the piston around it. It'll get so much pressure that'll pop out. So too much heat's a bad thing. but we use ethylene glycol because it has a higher heat capacity, even higher than water. So water does not have the highest. So you have things, ethylene glycol, propylene glycol have higher heat capacities. So, and we just, besides the fact of standardization, but I mean, Sahara Desert, I guess it does freeze in the Sahara Desert. Oh, never mind for that one. There are a lot of areas that never freezes. So, okay, so that's heat capacity. So you can look at heat capacity as an overall thing, and we'll talk about that in a few examples. And then there's specific heat capacity, which we use for many applications. Circulate the heat. Yes, Eli, you're right. And it does it more antifreeze does it more efficiently than water. Okay. Suppose you find a penny minted before 1982 when pennies were made of copper in the snow. How much heat is absorbed by the penny as it warms from the temperature of the snow, which is -8 degrees Celsius, to the temperature of your body, which is 37 degrees Celsius. So this is going to be your system. So you have to decide what your system is. So do I have, what color do I have? Okay, so here is my copper penny, and the copper penny is at -8 degrees Celsius. It's 3.1 grams. And then we have, all right, I guess I'm kind of pink. So we'll have the person here, and this is the person at 37 degrees Celsius. So, okay, if you, and the system also, the system, this direction into the system is positive, leaving the system is negative. If you call your system the copper, the energy flow is positive. So because your penny is going from -8 degrees Celsius to 37 degrees Celsius. The copper penny is absorbing energy. That direction is positive. If the person is the system, if you consider the person the system, the energy flow is negative. Because when you pick up the cold penny, so you pick up, you hold the cold piece of copper, the energy is going from your body, from your hand into the copper. So the energy flow for the human in this case is negative. So it depends on your system. And what is it asking for? How much heat is absorbed? Okay, the heat absorbed by the penny. So how much heat is absorbed by the penny? This is positive. So my answer from context, the energy is going to be positive. So the heat flow is positive. And so we do then the heat flow is mass times specific heat capacity times change in temperature. I don't know what the specific heat capacity of copper is. Well, okay. Let's do the numbers. 3.10 grams. What is the heat capacity of copper? I'll take a random question. It is 0.385 joules per gram degree Celsius. So this is the specific heat capacity. The change in temperature, change is always final minus initial. So your change here is 37 minus a minus 8, which is 45 degrees Celsius. So remember that change is always final minus initial. So we have 37 minus a -8. And you put that all in and you get 53.7 joules. Okay. So let's talk about some context here. So change being final minus initial. So think of it like money. So if you go to work and let's say you get paid every day, if you make $100 a day, and if your bank account balance at the end of the day is $1,100, and at the beginning of the day was $1,000, your change in money for that day is your final 1,100 minus your initial 1,000. So it's 1,100 minus 1,000 or positive 100, right? So that's your change in money, final minus initial. So same thing for temperature. The final temperature of the copper is 37 degrees Celsius. Your initial temperature is negative 8 degrees Celsius. So your total change is positive 45 degrees Celsius. I guess I should have emphasized the positive there. So, and then specific heat capacity here, you just, either memorize it or look it up, and then the mass. So heat is mass times specific heat capacity times change temperature, or also the mass times specific heat capacity. This is also your heat capacity. So think of, kind of like mass versus density. So heat capacity is kind of like mass, and specific heat capacity is kind of like density. So where you have an intrinsic, so specific heat capacity is intrinsic. So something like density, it doesn't matter how much stuff you have. And then heat capacity is extrinsic. It matters how much stuff you have. So you can also calculate heat capacities for things that you use, like calorimeters. So you'll learn about that later. And if you do a lab, I think usually we do labs on this. I can't imagine they're going to change anything. So, okay. And also heat capacity for water is 4.18 joules. So heat capacity for water, specific heat capacity for water is 4.18 joules per gram degree Celsius. So that's more than 10 times that of copper, right? So to show you what I mean by water has a high heat capacity, it's because it's just, compared to metals, and it's just above and beyond. It's a factor of 10. Also units. So I am certainly guilty of this. I look up heat capacities sometimes on Google, sometimes, dare I say, I look it up on Wikipedia. So, and the units are sometimes weird. Sometimes I like using joules per gram degree Celsius. Sometimes I see it in kilojoules per mole Kelvin. And you have to, if you look up units of something, you get it like you look up Wikipedia, like what is the heat capacity of aluminum? And it gives you in kilojoules per mole Kelvin. Like, oh crud. So you have to convert though. So in aluminum, for instance, it's 27 grams per mole. So you have to do dimensional analysis to convert this back. You'd have to use dimensional analysis to convert this unit into the unit that you want to use. The other thing is for multiplication and division, a degree Celsius is the same thing as a Kelvin. Okay, so unit-wise, when it comes to multiplication and division, you can use Celsius and Kelvin interchangeably. Okay, so magnitude though, how big it is, it's different. So, but if you're multiplying and dividing Celsius and Kelvin, you can cross cancel them. So keep that in mind if you are ever changing units on that. Moles and grams though, you have to then go to the periodic table and then calculate out. So, okay, I'm about 1 minute away from shut up time. Anybody have any questions about anything? Okay. Oh, there's my shut up alarm. I can feel it vibrating. All right, shut up alarm. Time to stop talking. And I do want to reemphasize, if anyone has any issues to come and talk to me, we want to see you through this class.